Conductance and Resistance. 29. Conductivity gives rise to conductance, and resistivity to resistance. For explicitness, let a conducting mass of any shape be perfectly insulated, except at two places, A and B, to be conductively connected with a source of voltage. Let the voltage established between A and B through the conductor be V, and let it be the same by any path. This will be the case when the current is steady. Also let C be this steady current, in at A and out at B. We shall have V equals RC, C equals K times V, where R and K are constants. The resistance and the conductance, taking the place of resistivity and conductivity, when voltage takes the place of electric force, and the current that of current density. The activity of the impressed voltage is Vc equals Rc squared equals Kv squared and represents the Joulean waste per second in the whole conductor, or the volume integral of Ec or of Ke squared before considered. Permittance and Elastance. 30. Permittivity gives rise to permittance, and elastivity to elastance. To illustrate, for the conductor, substitute a non-conducting dielectric, leaving the terminals and external arrangements as before. We have now a charged condenser. Displacement, that is, the time integral of the current, takes the place of current in the last case, and we now have d equals SV. V equals d over S. If d is the displacement, S the permittance, and its reciprocal the elastance of the condenser. This elastance has been called the stiffness of the condenser by Lord Rayleigh. It is the elastic resistance to displacement. The displacement is the measure of the charge of the condenser. The total energy in the condenser is half V times d equals half S times V squared, and equals half d squared over S. This means half the product of the force total and the flux total, between and at the terminals. It is also the volume integral of the energy density, half the summation of C times E squared. As the dielectric is supposed to be a non-conductor, the current is .d or S.V, and only exists when the charge is varying. But it may also be conducting. If so, let the conductance be K, making the conduction current Bc equals K times V. The true current, that is, the current is now the sum of the conduction and displacement currents. Say, tau equals C plus d dot, equals brackets K plus S d over dt all times V. This is the characteristic equation of a condenser. It comes to the same thing if the condenser be non-conducting, but be shunted by a conductance K. In a conducting dielectric the permittivity and the conductivity are therefore in parallel arc, as it were. It was probably by a consideration of conduction in a leaky condenser that Maxwell was led to his inimitable theory of the dielectric, by which he boldly cut the Gordian knot of electromagnetic theory. The activity of the terminal voltage we find by multiplying equation 5 by V, giving V tau equals V times C plus V times d dot. This equals R times C squared plus d over dt brackets half SV squared, representing the waste in Joulean heating and the rate of increase of the electric energy. Each of these quantities is the sum of the same quantities per unit volume throughout the substance concerned.